Um, JD did such a great job yesterday introducing himself, I won't even attempt to try and match trying to introduce him either. But our next speaker is Brian Becker, and he claims that he learned APL at the early age of 14, and now says that he's been doing APL for more than 3/4 of his life. So you can do the math and figure out what that means. And Brian has been involved with the APL problem-solving competition since its inception in 2009. And that predates his involvement with Dyalog. In 2009 and 2010, he was invited to be a judge of the competition. And then when he joined Dyalog in 2011, he continued to work on the competition, and it continues to be one of his favorite parts of the user meetings. So, if I did this right, duplicate. What's that? Okay. All right, so this is the prize ceremony for the 10th annual APL problem solving competition. And so the first thing I'd like to do is kind of review our history, go through the past, and talk about some milestones. In 2009, that was our first year, and Brooke Allen actually helped organize the competition, and it involved solving the first 20 problems on Project Euler. And the prize ceremony was held in Princeton, and again, that was my first involvement with the competition. In 2010, Dyalog took over writing the problems for the competition, and also added in some Rosetta code problems. In 2011, Joel Huff was the winner that year, and in his presentation about his winning entry, he mentioned that he didn't find anything called TryAPL. He knew that there were other programming sites out there to learn languages, and so that became the inspiration for the TryAPL site. In 2013, student competitions started helping us with hosting the competition, and we introduced the 10 phase 1 questions and then the more complicated phase 2 questions. And we also changed the name from an APL programming competition to problem solving, because really I think that's what the focus should be, is that we solve problems with APL, and at least my coworkers would admit that I'm not a very good programmer, but I'm an okay problem solver. And in 2014, we started recognizing, we always had a number of entries from people who were not students. The competition was organized primarily to try and attract new APLers, but we had a number of people who already knew APL in their professional lives that would submit entries, and we wanted to try and recognize their submissions as well. And then in 2016, we switched to having some domain-specific phase 2 question types. So, now the other thing I'd like to do is to talk about some of our alumni from the competition. The very first winner, Ronald Chan, actually interned at Dyalog for a while and contributed some work on the interpreter. I think in Domino, if I'm not mistaken. Is that correct? Yeah. And the next year, or when Ryan Tarpine won, he contributed a number of the problems for the following year's competition. And those were some of the best problems we've ever published. They were quite good. And I don't know why it's double clicking, but that's okay. Joel Huff, who won the following year, again, he was the inspiration for TryAPL, but then he co-presented at a conference with Morton on why APL is so cool. So, Marinus Oosters, who won a few years ago, did some work with Dyalog and produced the Pineapple Python interface for Dyalog APL. And then we've got Josh David, who's here with us this year, and he's done some interning and work with the Carlisle group. And then we also have Zach Batik, who is the chief APL developer at RiskFlow, and Zach contributed a number of the problems for this year's competition. So we've gotten some good feedback and some good mileage out of our past participants. Now, if we look at this year, again, we had 10 phase 1 problems. And so here's one of them. Here's problem number 1. Imagine you're standing in front of a line of skyscrapers of varying heights. And you can always see a skyscraper that is taller than a closer skyscraper. So how many skyscrapers can you see? Okay, so what would be an APL expression to come up with for that? So we won't mull over that for very long. Another problem, problem 10, was write an APL expression that given right and left arguments of character vectors, discounting spaces or punctuation, you'll return a 1 if both arguments are anagrams of one another. So this was actually kind of interesting. There was a variety of kind of neat solutions here. One of them was to use a function and an operator, right? Take out the spaces, sort them both, and then do a comparison. And another was, and again, we won't linger on this too long, but if you want these, they'll be on the slides. Also, we had our phase 2 categories this year were in cryptography, neural networks, and physics. And I always like to try and reflect some of the reactions that we got back. We asked for feedback from the participants every year, and so this is some of the feedback that we got. Problems were engaging enough to keep me awake until midnight, and it was the eloquence of APL that kept me coming back to where I had left off. The problems were intriguing, their descriptions comprehensive, and accompanying examples illustrative. Above all, learning APL itself was a breeze. Rats. I had a hard time when I was 14 years old, so a few words about APL. APL codes tend to be terse. For instance, a single line of APL can accomplish what other languages can't in 10 lines of code. Besides being intuitive to implement, APL programs are easy to debug. So he's clearly never tried to debug salt. Another one said, I enjoyed all of the competition problems I solved. This is my first exposure to real problem solving in APL, and it has been a wonderful, though sometimes foreign, or oftentimes foreign, programming language. And then my favorite, I like brevity. APLers like brevity, really enjoyed the contest. So in the future, well, we're always looking for new problems. And so what we look for is problems that highlight the strengths of APL and have a definitive solution. We've had problems in the past where we've had to do simulations. And the problem with simulations is you can get a wide enough range of results that it makes it a little hard to judge a lot of entries if we happen to get them. And then we're also looking at, every year we do an evaluation of each year's competition. And so we might, look at changing the way we've been hosting the competition or the types of problems that we're going to be giving out, and maybe the timing of the competition to make it overlap better with the academic year. So again, if anybody has any type of suggestions or wants to contribute to those efforts, please let us know. So we can't run a competition without a lot of help. And I want to thank Fiserv, SimCorp Italiana, and our anonymous sponsors for their support since the beginning of the competition. So for 10 years, these generous entities have been supporting the competition financially. Dyalog, of course, has been coordinating and hosting it, but to subsidize the prizes and people's travel and things like that, we just couldn't do it without your support, and so we thank you very, very much. I want to thank Student Competitions for hosting. We've had some ups and downs with them, mostly technological things with getting them to host an APL-based site, but and every year we seem to go through the same, they turn over enough staff every year that there's no institutional memory, it seems. So, but hopefully maybe next year we'll solve that problem. And I'd like to thank Zach. Zach, where are you? Someplace? I can't see. There he is. Zach contributed a number of the Phase 2 problems this year, and from a nice variety of problem sets, very interesting problems, and so we really appreciate his contributions. I'd like to thank Roger. Roger contributed a number of the Phase 1 problems or ideas for the Phase 1 problems, and he also wrote an excellent blog post, which if you haven't read it, go out on the Dyalog blog site, and where he talks about the 10 Phase 1 problems and describes their solutions. So I want to thank Adam and Mikhail for helping judge the entries this year. We had a lot of entries, and there was a lot of stuff to go through. Adam actually automated a lot of the Phase 1 judging, and populated a spreadsheet with color. It was great. So that helped quite a bit. And finally, I want to thank Fiona. She helps just keep things organized. She was my main go-between between myself and student competitions. And so she got to deal with flack coming from both sides, and she was a nice buffer there and kept things flowing smoothly. So now we can talk about the results. I'm actually running way ahead of time. I don't know how I managed to do that. So for Phase 1, we had 42 entries, and 26 were from students. And for Phase 2, we had 28 entries, and 20 were from students. And most of I think all of the Phase 2 entries had also submitted Phase 1, right? So in third place, we have Rafael Rodriguez Rocha de Melo. And when I read Kyoto University in Japan, there seemed to be an incongruity there, but indeed, he is studying in Japan. In second place was Lynn van Houwe from the University of Antwerp. In first place, in the professional category, the non-student category, we've got Tiziano Berghi, and from SimCorp Italiana. And Tiziano, if you're here, yes? We have a certificate for you. Congratulations on a great entry. And in first place in the student category is Alva Björk from Uppsala University in Sweden. And I would like to ask Lavinia Zivith to come and present Alva with his prize, and then Alva will tell us a little bit about the work that he's done for the competition.
Thank you. This is very nice.
Yes. So just a little word about, I'm Lavinia Zivit from Fiserv, and as Fiserv member of the APL team, we are very honored and pleased to have been involved with this competition since day one. So it's incredible to know that it has been 10 years. And over the 10 years, students from 8 different countries have been, won the grand prize and have been part of these user conference and present their creative and very thoughtful process of using APL as a very unique tool to approach problem solving. So it has been fascinating over the years to see all the students that come through the door. So this year we're very pleased to have Alva Björk, and I've learned to say your name properly, and to share with us his process and experience in learning. Thank you.
Thank you. And Alva says that he has got his own little biographical background to present during his presentation. So without further ado, Alva.
Thank you. So this is my first presentation proper, so please bear with me. we go. And let's go there. Okay, it's working. Let's see, where am I? There am I. No, no, full screen. Oh, full screen. 1.6. I'm doing something very strange right now. What is happening? There we go. Okay, cool. And I'm gonna do this. There we go. Okay. Yes. Yeah, so that's the solution, I guess. Moving on. My name is Alve Björk. I come from the Kingdom of Sweden, and there I am a perpetual student at Uppsala University. Some things I like include tea, cats, murder mystery television shows, mainly British ones actually, and computer science, of course. But for the last half year, my life has mostly revolved around catering for this little person, which so the competition was very good in that it gave me something stimulating to think about for a while. So the contest this year, as Brian told you, yeah, it's still 2 phases. The first phase is one-liners, even though admittedly some lines are quite long. Phase 2 is mostly couple-liners. I didn't quite manage to do that for all of the problems, but there were 3 tracks this year you could choose from. 3 problem sets. The first one was on cryptography, the second one on physics, and the third on neural networks. Each problem set had a set of problems, obviously, and each problem had a set of tasks. I don't have time to speak about everything. And if I did, I think I would bore you to death, so I'm not going to do that. I've selected a few problems I will present. But I've actually written slides for most of them, so I don't know if you have sort of looked at the problems, but if you have, I can probably bring that up at the end if you have requests. This was the first problem of the physics part. You were asked to calculate the aphelion velocity given the perihelion velocity and the perihelion distance. I have no idea what this means. I think it relates to planets somehow. It's science. Luckily, you're provided with a formula, and that is math. I know math. And it boils down to solving a quadratic equation, which all of us have been able to do for quite a long time, so I'm not going to dwell on that. And you were actually also supposed to round the answer, but then you needed a non-rounded answer in another task, so that's why you have 2 functions instead of 1. For some reason, when I did this in Dyalog, the editor insisted on expanding one of the numbers and making it 20 digits long. That was very annoying. But the reason I bring up this problem was because that is so neat. Honestly, it was not obvious to me at first. I thought about how should I deal with plus minus, and then when I somehow did this, yeah, it's beautiful. It's so not only is this probably the most obviously readable way to do this, but it's also general. This is not a special case, and that really makes it much better in my mind. Yeah, I like trains. I think I will actually do all of the physics problems in order. They were the easiest set. The problem sets were quite, so I did all of them in the end because I liked it. But they were a very sort of, the physics one was easier and the crypto one was harder. And the neural network one was somewhere in between, I guess. But sometimes with the problems, just sort of reading the description and trying to figure out what you were supposed to do was a big part of the problem. But I'm sparing you that because it doesn't make for a very good presentation. So I have sort of rewritten the problem statements a bit. So in this one, you had something called a grid. It's a character vector, no character matrix. It can have boxes or dashes or crosses. And then you're interested in the shape made out of, so sort of the shape the boxes make in your grid. And you don't really care for the dashes or the crosses. So here are four grids with different shapes, which you might recognize, maybe. And we are interested in some properties of these shapes. So a shape is symmetric if you can sort of rotate it half a turn and it stays the same. And it's contiguous if it's if all boxes are adjacent. And it's valid if it is both of those things. But this is not a formal definition. This sort of is a loose definition at best, especially the contiguous criterion. But that was kind of also the problem. So the solutions to the problem was to specify formally in APL how to do this. Oh, and this is, so that's why I did 4 of them. So I can have examples of all of them. So contingency doesn't work diagonally. It has to be horizontal or vertically. And also symmetry doesn't have to be it doesn't have to be centered in the grid. It can be off-centered. So the first task was about symmetry. This is what I did. So first I consider only boxes. I think the reason there were dashes and crosses to begin with was a bit of a red herring. I don't know. And then you cut out the shape. So so you center the sort of the shape. And then you compare the vertical and the horizontal rotation. This is probably my second favorite train from what I submitted. It looks cool. It's like a Death Star and beams coming out. Contingency was a lot harder, for me at least. So my first idea was to try to implement some kind of disjoint set, union find kind of data structure and use a reduce and stencil to successively merge cells. But I didn't like that. Union find it's a really cool, but it's also inherently stateful, which and I had a feeling that it would take quite a bit of code, so I just didn't write the code. I had the idea, but then I didn't bother implementing it. But after a while, when it had rattled around in my brain for a bit, then I came up with a much better idea. So instead, you consider the shape as a graph, and what I mean by that is to sort of take one of the shapes and zoom in a bit. I mean this. So your boxes are your nodes, and they are connected if they are adjacent. And to make it more, a little bit more concrete, we will name our boxes with their coordinates. So there we go. This is not too hard to do. So once again, you just consider the boxes. And then you compute the adjacency matrix for the graph by doing the selfie outer product with the property of being close. I do include self loops in this, so it's not a graph proper, I guess. But it works out good because when I so the thing with adjacency matrix is that if you have one and you multiply it with itself, you get a new graph modeling the relationship of having a distance of a path of distance 2 between any two nodes. But actually, if we have self loops, it will be a distance of 0, 1, or 2. And if we multiply again, it will be 0, 1, or 2, or 3, and so on. So taking the least fixed point, we get the transitive closure quite easily. And once we have that, we know that, well, if the graph is connected, then we should end up with a complete graph. And a complete graph is all ones. So that's easy to compare against. I was very happy when I found this solution, that I didn't have to write like mutation and. But then when I look at it now, I think that maybe the the selfie Swedish tilde should have been inside the power somehow. That would have been better. Yeah, that probably has a fancy name. I'm sorry. I just recently learned that these are called defuns and not sort of curly bracket functions. The takeaway for me was that if your problem domain has some connection with the linear algebra, then you should probably exploit it. Validity is super easy once you have symmetry and contingency. It's just that, and it could not be more readable. I even think this is better than mathematical set notation, because in set notation, once you move from sort of elements to sets, you have to change notation from the wedge to the union. But in APL, you don't have to. Yeah, I'm doing this a lot quicker than I anticipated, but I have a lot of problems. So that's if you enjoy it, I don't know. Yeah, so this is mostly to get to the next one, because we will need this. Anyways, so you have a matrix, probably a large one. I think the examples in the were 40 by 40. Well, that's not large to you, but I don't know. And they are ones or minus ones, and then you're supposed to calculate something. Once again, some physics thing. I think this is smaller than the thing before, but I'm not totally sure. But you get the formula once again. So you're taking the sum over all adjacent pairs, and then you are negating it. And actually, this negation was left out of the examples in the. So the examples were wrong from the beginning. But this was pretty much made I felt, for a stencil. I don't think this is as concise as this could have been. I remember being a little bit bummed that I had to do the each on omega and the transpose omega instead of. I wanted to have the each inside on the 0,2. So I do like each of 0,2 and 2,0. And yesterday I figured out that maybe now that I've learned a bit more, I can actually get that working. But then I didn't even get this working for some reason. So that didn't work out very well. Maybe you guys just see what is wrong here. I'm not sure if I think this is what I submitted, but I can't get it working now. Anyways, so that is used in this problem, which is very, this is well specified compared to the other ones. It's sort of do this, write a simulation, you take an initial lattice. Well, you don't actually take the lattice because you're given the lattice, but you know its size. And then you choose an element and flip it, and if it and calculate the change in energy, I guess. And you accept it either if it's negative or with some probability if it's positive. Do this n times. Return the new lattice. I think it should say not map. And I could translate this literally. So I pick an index and I flip the bit. I love that you have the @ operator. That's it's really nice. The only thing with that operator is I don't really see why you cannot use both indices at the same time. You have to do one. At least I never managed to. I think it has to be a vector, I and j, or like, yeah, something like that. I calculate the total energy for the old matrix, no, the new matrix and the old one, yeah. And then what is nice is I even get to merge the two conditions on keeping it or throwing it away. Because it turns out that if it's negative, yeah, the comparison will always be true. So then you don't have to worry about it. This is super nice because it mirrors the definition almost exactly. The downside is that it's really, really slow because you have to copy the matrix each time since you need to keep the old one if you're going to do that. And, you know. So I guess you can use this as a reference implementation for your pass-through code later on. Or maybe if you don't care about performance, just about price money, then this has also worked out great. Let's not do that yet. Since I have a... Let's do another one. Does anyone have any requests? I wanted to do the neural network thingy, but when I prepare the slides, it is quite complicated to explain, and I only remember it. Like, I remember what I did, but not why anymore. We can, okay, I'll do, okay, the cracking or the encryption. Well, we can do both. We can start easy. So that is problem set. The XOR is in the first problem of the first problem set, I think. I'll just go there. Oh yes, didn't even crash. Okay, yeah, this was not that. Here is the first one. This was a little bit too easy. Exclusive OR is just addition in C2. This is a funny kind of thing, notation-wise. That's not this either. Let's see. Here we have encode. That's getting to the encryption stuff, right? So this was, I think, as like the other problem was about sort of discovering stencil, I think this was about discovering encode and decode, because that's pretty much all you need. And then you also need the inverse, even though they didn't tell you. Oh, and also I did, that was not part of the, this is not what I submitted. This I did when I prepared my slides, I was like, this should be a train, and it looks nicer as a train, it turned out. No, sorry, this is not the encoding. This is the actual encryption. Where did the UTF-8 bits go? Whatever, I think this is the fun part. So you're supposed to, you did your encryption, right? But now you're supposed to undo it. Maybe you forgot the password, but luckily you're very bad at choosing passwords. I had a lot of interesting ideas about how to do this, but that felt a bit unnecessary. So the key space is super duper tiny, so it's very easy to just generate all possible keys. Okay, check. Generate all possible plain texts. Check. And then I score the plain text according to the collinearity sort of their character distribution. So the way I think about this is that the character distribution is a unit vector in 26 space. And then you have the character distribution, which Wikipedia claims is holds for English. And for each plain text, I think what I'm calculating is the cosine of the angle between those vectors. And then I pick the one that is closest. But there's a big disclaimer on this. I'm not a statistician. I have no idea if this actually has merit, but it worked, so that's good. I'm also doing some unnecessary stuff like sorting everything when I only need the index of the maximum. But it worked. It was quick on my machine, so that's fine. The next one is one I didn't prepare. So let's go somewhere else. Let's go back to the GCD maybe. I think that's okay, I'll just restart here. Oh yeah, here we go. So one of the problems was write GCD but make it work for arrays. Okay, and the thing I came up with looked like this. So I have done the colors wrong. I'm sorry about that. But basically, you take the difference, or the distance, not the difference, and then you take the minimum and you recur until you get only zeros in one of the arguments. And that, I thought it was pretty neat when I wrote it. When I came back to it, I think it's a bit incomprehensible. But the problem with doing, so this is like the usual way to do GCD, right? But the problem is that you might get oscillations. So you get zeros, but they move back and forth. But there's actually nothing to stop you from using rank, and that works fine. I think that should have been the solution. I'm not sure if this would work in parallel. Does max work in parallel? I think it's doable with bit hacking, but maybe not for floats and stuff. Yeah, we did that. Let's look at some more code then. Next prime. Oh, next prime was fun, in a sense. I have a primality, yeah, checking function that does very much it's like very readable. Should be larger than 1 and not divisible by anything in the range from 2 to the square root of n. And the next prime takes successor until it finds a prime. I also find that, well, since I wrote it, that might be the reason I find it very readable, but still, I can still read it. That is good, right? I ended up doing everything in this, with only defense and only single assignment, no mutability, no thread funds. But that was not really a conscious choice. It's just the way I like to solve problems, I guess. And I actually, before the competition, I had two, well, this is not strictly true, but almost, 2 exposures to APL. I had read Ken Iverson's paper, and then I had also seen the Game of Life, on YouTube. And in that video, it's only defense, right? So that's what I thought that APL functions were. When I discovered thread funds, it was weird. Yeah, okay.
Please go ahead and start lining up.
I'll go to the wrap-up part. I just have a few reflections. I think APL is a ton of fun. I think getting proficient when array manipulation has been challenging, but that's kind of the point. I feel like I'm learning a lot, and I'm learning fundamental things. The funny squiggles and the non-conventional grammar has not been a problem at all. I kind of like it, actually. What I don't like is like the incomprehensible system functions and referencing things by numbers instead of names, and this. That I feel is arbitrary, and I don't want to have to learn it. I'm also still having a hard time adapting to the session, and I've complained to a lot of people around the room about that, I think. Also, as you may have noticed, when I explain the code, I go from top to bottom, but from right to left. And that works fine for reading code, but it's a hassle to write code that way. I actually spent an afternoon seeing if I could change the APL Unicode characters to be right to left in my Unicode database, but that turned out to be way too hard. And then yeah.
All right, so basically I have only one comment, which is I absolutely love these slides. These are great. Yes, these are right. And other than that, I also like that comment about the linear algebra, because at least if my linear algebra instructors were correct in the way they described linear algebra, pretty much everything has some linear algebra to exploit. So.
Yes, and even if it does not, if you're an engineer, linear algebra is what you can actually work with, so then you approximate stuff into linear algebra, I think. Yeah, exactly. Sure. Okay, yeah, not just engineering. The slides are unfortunately not done in APL, but if it's any consolidation, the maze on the first slide was done in APL.
Go ahead.
Just 2 comments from your presentation. First of all, I think the insights are wonderful, and your coding style is elegant, and I think most of the people here would have trouble improving on what you've written there. Thank you.
Thank you.
Any other questions? Okay, in that case, I guess we've got a break coming up for the next half an hour. If you could reconvene here at 15:30, we will see you then.